Good to everyone. My name is G. Saitaya. I am studying SRIT College, ECEC section. I will explain about the interference in film briefly. First of all, I am thankful to our Honorable Bharati Madam for giving this golden opportunity. Today I am going to explain briefly about interference in thin film and the application and examples based on interference. The magic of thin film interference, a colorful phenomenon. What is interference? Interference is a fundamental wave phenomenon when two or more waves superpose to form a result wave of greater lower or the same amplitude. When waves meet, they twist and toughen leading to specular effects. Wave superposition, wave combine when they overlap, amplitude changes. Resultant waves can be stronger or weaker. Visual effects. This interaction creates observable patterns. Introducing thin films. Layers of light. A thin film is layer of material, typically only nanometers or micrometers thick. When light interacts with this, it undergoes a fascinating transformation, creating the vibrant colors we often observe. Microsoft layers. These films are incredibly thin, often just a few wavelengths of light. Light interaction. Light reflects and refracts multiple times within the film. Colorful results. This interaction causes specific colors to be enhanced or cancelled out. Key players. Light waves reflection and key players. Light waves reflection and diffraction. Understanding how light behaves at the boundaries of a thin film is crucial. Light wave interact with the film's surface through both reflection and refraction, setting the stage of interference. Incident light. Light waves strike the surface of the thin film. First reflection. Some light reflects off the top surface. Refraction transmission. The rest of the light enters the film and bends. Second reflection. Light reflects off the bottom surface of the film. Emerging waves. These reflected waves meet and interference. Constructive interference of brightness amplified. When two light waves combine in phase, meaning they crest arguing with crescent with throws, their amplitudes add up. This results in a brighter, more intense light of a particular color. And wave alging perfectly, they reinforce each other, leading to increased brightness. Crest meet crest, trough meet trough. Amplitude combine producing a stronger wave. This amplification creates the vivid colors seen in the films. Think of two people pushing a swing. At just the right moment, the swing goes higher. The phenomenon is responsible of the brilliant hues you observe. Destructive interference, where light disappears. Conversely, when two light waves combine out of phase, where the crest meets a trough, they cancel each other out. This results in a reduction or complete absence of light, creating dark areas or suppressing certain colors. When waves oppose each other, they diminish or cancel out, leading a darkness or color suppression. Next meters reducing amplitude energy is redistributed, not destroyed. Areas appear darker, specific colors are absent. Imagine two people pushing a swing at opposite times. The swing barely moves. Destructive interference plays an equally important role in shaping the colorful pattern we perceive. The role of thickness and wavelength change. The specific colors produced by thin film interference depend critically on two factors: the thickness of the film and wavelength of the light. A slight change in ether can dramatically alter the observed pattern. Film thickness determines the path difference between reflected waves, light wavelength. Each color has a unique wavelength, resulting color. Specific colors are enhanced or suppressed. Angle of view affects the perceived path difference. Everyday wonders, soap bubbles and ILC. The dazzling array of colors in soap bubbles and IL6 on water are classic examples of thin film interference in action. These everyday phenomena beautifully illustrate the principles we have discussed. The varying thickness of the soap film or oil layer causes different wavelengths of light interference, constructively and destructively at different points, creating a dynamic kaleidoscope of color. Soap bubbles. The film thins as water evaporates constantly, changing the colors. Oil slicks. The uneven oil layer creates irregular, swirling color patterns. Applications of thin film interference coatings to sensors. Beyond their natural beauty, thin film interference principles are harnessed in various technologies, from anti-reflective coatings on lenses to advanced optical sensors, showcasing its practical utility. Anti-reflective coatings reduce glare on camera lenses and eyeglasses, solar cells, enhance light absorption from increased efficiently. Optical filters selectively transmit or reflect specific wavelengths of light. Chemical sensor detects substance by changing its reflective properties. Conclude seeing the world through a new lens. Thin film interference is a beautiful intersection of physics and art. The ephemeral beauty of soap bubble to critical technology application, it reminds us that the world is filled with hidden wonders. Revived by light's intricate dance, fundamental principle explains vibrant colors in nature. Key factors: thickness and wavelength drive color repetition. Practical uses: enables advanced optical technologies. Everyday beauty transforms the mundane into the magnified. Enhance the colorful complexity around you.